Hi and welcome. In this video, we are going to introduce some types of convergence of sequences of random variables. Let's start with an example of a sequence of random variables x1, x2, x3, and so on, each of which has a normal distribution with mean 0 and standard deviation of 1 plus 1 over n. Xn, in other words, has a normal distribution with mean 0 and standard deviation of 1 plus 1 over n. For example, x1, when n is 1, this has a normal distribution at mean 0 and standard deviation of 2. x2 has a normal distribution of mean 0 and standard deviation of 1.5. x3 has a normal distribution of mean 0, standard deviation of 1.3, and so on and so forth. As we increase the n, which is the size of the sample or the number of elements in this sequence, for example, x of 1000 will have a normal distribution with mean 0 and standard deviation of 1.001. Now we see that as we increase n, the standard deviation of the sequence converges to 1. It's 2, 1.5, 1.3, and so on and so forth. The greater or the larger is the n, the closer the standard deviation gets to 1. And that's not a surprise because as we increase n, this part of standard deviation goes to 0. And finally, if we take the limit of n going to infinity, which is the limit of the sequence, this 1 over n goes to 0, and we are left off with a distribution, a normal distribution with mean 0 and a standard deviation of 1. A similar example here, check this example x1, x2, x3, and so on, which has a normal distribution with mean 1 plus 2 over n and standard deviation of 2 plus 1 over n. Then the same way as we increase n, obviously that would then affect both the mean and standard deviation. You see that the sequence approaches to a normal distribution with mean 1 because this part would go to 0 and a standard deviation of 2 because this part would go to 0. Considering these two examples, let's define the first type of convergence of sequence of random variables, which is called convergence and distribution. Consider a sequence of random variables y1, y2, y3, and so on. Then yn, which is a sequence representing this sequence of random variables, is said to converge to y, which is another random variable, and distribution if ny converges to fy, and as shown as follows. And this is nothing but those examples which we have seen. And in these examples, we have seen that the sequence converges to a particular random variable with a particular distribution as n grows large. For example, in here, this sequence converges to a random variable x, which has a normal distribution 0 and 1. In fact, this is a standard normal distribution. And in this example, this sequence converges to this random variable, which has a normal distribution with mean 1 standard deviation of 2. And this random variable with this particular distribution is called the limiting distribution. This kind of convergence is called convergence and distribution. We have a couple of other convergence as well. For example, convergence and probability. A sequence of random variables x1, x2, x3, and so on converges in probability to another random variable x, shown by xn, this p here, x, if the limit n going to infinity of the probability that xn minus x is bigger than a positive number goes to 0. For all epsilons bigger than 0. The intuition behind this limit is the following. As n goes to infinity, the chance that xn departs from x is going to 0. That means the probability that xn goes away from x is actually approaching 0. In other words, putting it in a kind of reverse order, as n increases, the probability that xn gets closer and closer to x is actually almost sure. For example, if you take xn that represents coin toss and let xn be 1 for head and xn be 0 for tail, furthermore define xn bar to be 1 over n, the sum of xi's, then we know that the expected value of xi is 0.5. Since this is a fair coin and there's a 0.5 value for, or the average of 0.5, which is between 0 and 1, then xn converges to 0.5 in probability. The intuition behind this example is that you flip a coin more and more times, and the fraction of heads here approaches to 0.5 with high probability. Since this is a fair coin, you would expect that as you repeat this experiment more and more times, that means as n goes to infinity, the number of times that you get hit is 50%, and the number of times, of course, you get tail is 50%, and that's with a high probability. Or in other words, the probability that xn departs from 0.5 here goes to 0 as n increases. Another type of probability convergence that we have is convergence in mean square. A sequence of random variable yn converges in mean square to another random variable y if the limit of the expectation of yn minus y square is 0. That means the difference between yn minus y all square, and if you take the expected value of that, is approaching to 0 as n approaches infinity. And it's shown by yn, this m, then y. That is, the distance between yn and y approaches 0 as n grows large. That's the basic idea. If a sequence of random variables approaches or converges to y in mean square, this implies that this sequence also converges to y in probability. That means convergence in mean square automatically implies convergence in probability. And on the other hand, convergence in probability implies convergence in distribution. That is, if you have a convergence in mean square, automatically you have convergence in probability. And if you have convergence in probability, automatically you have convergence in distribution. That is, the strongest type of convergence is convergence in mean square, followed by probability and followed by distribution.